So, good morning, everyone. In our last class, we have been discussing about discrete Fourier transform. Today, we will be talking about the fast Fourier transform. Okay. So, basically, fast Fourier transform it is not a transform in itself. It is a misleading name. Uh, However, it is just a method to implement discrete Fourier transform. Okay, so it is a faster way of performing discrete Fourier transform. Okay, so fast Fourier transform it can be implemented either by the method regarded as decimation in time, in short we call it DIT FFT, or decimation in frequency DIF FFT. Okay, so in either of these we use an architecture which is regarded as butterfly architecture. Okay, so a butterfly architecture it looks something like this. Okay, so this architecture it is regarded as butterfly architecture. So if we consider a 2 point this DFT, so herein say we have an input A and B, where input A and B are nothing but xn equals to AB. Okay, so when we are implementing this DIT FFT, then this input should be in the decimated order when we are implementing. Sorry. So I was telling you, suppose when we are implementing DIT FFT, we basically need this action in the decimated uh, order in the time domain. Okay, whereas your output domain, which is in the frequency domain, they remain in the same order. Okay, whereas when we talk about decimation in frequency, the frequency components they become or they come in the decimated order, and our input is in the normal order. Now the big question comes, what do we mean by decimated order and the normal order? Normal order is nothing but I give you a signal. दरवाजे को बंद कर दो तो एसी चल रहा है, बंद कर दो जस्ट ये. So the normal order is xn equals to x0, x1, x2, x3 and so on. So this is the normal order. So our time unit it would be 0, 1, 2, 3, 4 in the normal this increment it is going on. Now what is decimated order? Decimated order, let us take an example where we have xn which varies from x0 to x7. Okay, why I have taken a signal which is having a length of 8? Because when we are talking about this FFT, the FFT can be implemented when the signal length is equal to 2 to the power n. If it is lower than that, then we have to pad up the signal. Usually we do the zero padding. So by zero padding, we have to make the length of the signal such that it comes out to be at the value of 2 to the power n. Okay. So for the sake of my convenience, I have considered this length to be 8, which is equals to 2 to the power 3. Okay. So suppose we are having this signal xn, which is equal to x0, x1, x2, x3, x4, x5, x6 and x7. Right. Now decimation means what we discussed in our last class. Decimation means you are breaking down the signal. Okay. So herein what we will be doing, we will be taking all the even components on the right hand side and all the odd components on the right, on the this right hand side. So or you can say if you go by the time index, it is the even, or if you go by the element index, so these are odd values. So let us go for the odd values, odd indexes. So we name it like that. So x0 is the first odd index, so it comes over here. The next odd index, that means this is 1 2 3 4 5 6 7 8. Okay, so the next odd index is x2, it comes over here. Next odd index is 5, it comes over here. Next is 6, it comes over here. Similarly, we will be taking up all the even index values on the right hand side. Okay, now again we will decimate it. Okay, so again x0, x4, x2, x6. Similarly over here we get x1, x5, x3, x7. Okay, and suppose if it is say if it is a we are having a length of say 2 to the power 4, then we would be having the 16 values. We have to repeat this process until and unless we get a pair of signal components. A pair of signal components. Okay. So when we get this pair of signal components, now we will take this in this decimated order form. That means, see, x0, x4, x2, x6, x1, x5, x3, and x7. So when we are taking it in this order, then this order is regarded as the decimated order. Okay, this order is regarded as the decimated order. So what I told you, suppose I am considering DIT FFT. In the DIT FFT, what I said, as the name suggests, decimation in time FFT. So the input would be in the decimated form. Okay, and your output would be in the normal order. So what do you mean by normal order? We will be having xk equals to x0, x1 to x of 7. Okay, this is the first important thing what you need to remember. In the case of DIF FFT, that means decimation is in the frequency domain, and we have output in the output would be the frequency component. So the output would be in the decimated form and input would be in the normal form. Okay, so in a DIF FFT, so the order in the time domain is normal, and in the DIF FFT the output it would be in this fashion: x0, x4, x2, x6, x1, x5, x3, x7, which is similar to the DIT FFT, whatever is the input sequence. So similar to that sequence, in this decimated form we will be getting output. Now the butterfly architecture, uh, this is the basic butterfly architecture, and this is implemented for the DIT FFT. Okay, so what you have the inputs A and B. So it is there. Then what you will do, you will draw a straight line. Okay, then there will be a crisscross of the again. So what are these lines? These lines are the what do you call, the paths for the signal transmission. Okay, the paths for the signal transmission or the number transmission, whatever you say. And then we have this total factor over here. Okay, so let's see, say for example, if it is a dash equals to, we are having a, so there is nothing, so this a, it is coming over here as it is. Then we have b, it is getting interacted with the total factor, that means it is getting multiplied with the total factor, and then it is coming over here, so we are getting positive. So here there is a this what do you call, conjunction node, where two signal paths, they are meeting each other, so it constitutes the addition. So we have the addition of what, b of wn. Okay, similarly, say if you have the b dash equals to a, it is coming, then b wn, then we have a multiplier of -1, so it becomes a minus of b wn. Okay, any doubt over here? Good. So when we talk about this decimated order, sorry, the same order can also be regarded as the bit reversal order. Why? Suppose I am having these values x0, 1, 2, 3, 4, 5, 6, 7. So we can represent this 7 into 3 bits. So I can just break it down: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and triple 1. Now what I would do, I would reverse the bit. So uh, this one comes here, middle one stays here. So see, same thing. So we are just making the LSB as the MSB and MSB as the LSB. Okay. So if you do this and then you again calculate this order, you will find you are getting the same order as that of the decimated order. Okay. So decimated order and bit reversal order, both are the same. Now in DIT FFT, so I already told you, say we are having this butterfly architecture. So let us take an example of the 2-point system. In a 2-point system, we are having xn equals to x0 equals comma x1, right? Now if you decimate it, it will be the same, right? So we are having x0, x1, then we are having this butterfly architecture. This is w02. W02 is nothing but 1, right? So we are having x0 equals to x0 plus x1 multiplied by w02. So we get capital X0 equal to x0 plus x1. Whereas x1, capital X1, it would be equal to x0 minus x1, because there is a -1 multiplier. Okay. So this is a 2-point FFT. Now, when we want to go for 4-point FFT, what this method does is that you have put the order in the decimated form. Initially, it will perform two 2-point DFT. Okay. Initially, it will perform two 2-point DFT, and then the outputs of this will be taken to perform one 4-point DFT. Now, think of the condition. If you want to go for the, say, 8-point DFT, then there will be 4 2-point DFT, then there will be 2 4-point DFT, and then the output of those 2 4-point DFT would be taken for performing the 8-point DFT. Okay. So let us take the example of the 4-point FFT first. The first thing is that initially we will be breaking this down into two parts. because first we need to do 2-point DFT, right? So we will be taking x0 and x2 for performing the 2-point DFT. I hope all of you know how these values are coming. A equals to x0 plus x2. Okay, W02 is 1. So x0 plus x2. And this B equals to x0 minus of x2 because of this minus 1. Similarly, we get C and D values. Now over here, we have got this. Now what we have to do? We have to perform 4-point DFT. Okay. Now, once you are trying to perform the 4-point DFT, so you are using all the 4 points. Again, you have to find out this midpoint over here. Why this midpoint is important? This midpoint is important because before this, above the lines above this midpoint, they will be having total factor values of 1, and the below the thing they will be having the actual total factor values. So over here we are performing 4-point DFT. So if you see these lines, they are containing W04. Why W04? Because we are performing 4-point DFT. The next total factor it is W14. Are you getting my point? W04, W14. Done. So how will the connection now be moving? From the first line below the midpoint, it would go to the first point in the upper sections. So see, from here to here it is going. Let me take another pen. So from here, first line to first line it is going. Okay, to here. So if you say this is first line, this is second line, again this is first line, this is second line. Okay. Similarly, from first line to first line, again from first line to first line it will come. This again, the top one does not contains any total factor, so there is nothing. So below the midpoint we are having this total factor W04, and this C it will be multiplied with this W04 and it will be coming over here. So from here we are getting A plus C. Okay, because here it is 1. Now in the second in the next year, so from point 2 to point 2, what you will be getting total factor is W14. Then this from the signal will cross from this line 2 to line 2 over here, and vice versa from top to bottom we will be getting. Now over here what you are getting, x1 equals to, we got B over here, B, then what is W14? W14 is nothing but minus J, so minus J multiplied by D. Similarly, at the bottom half you get B minus of minus JD, so it becomes B plus JD. Any doubt? It is very simple. Anyone having any doubt, please ask me. Initially, you break down the signal components in two components into two parts. You perform the 2-point DFT using this butterfly architecture, right? Once you have done, you get 4 points. Now, in the 4 points, you divide it by the middle line, and you number the lines as 1, 2 in the same order. Top one, 1, 2, second one, 1, 2. Okay. Now connections would flow from 1 to 1 in either of the directions, and the top one it will not have any total factor because in the this butterfly architecture, the top part it does not have any total factor. The only the lower connection or the lower line from where the signal flows, it would be having the total factor. So the lower lines will be having the total factors. So A plus C, then we get A minus C because of the minus 1 multiplier. Similarly, from 2 to 2 when we will be doing, it will be W14. So it is going B minus JD and the lower line One is B plus JD. Okay. Another important thing before we move into the 8-point DFT. So if you see our total factor, it is this one. It is over minus j 2 pi kn by capital N. Okay. What is this 0 1? 0 1, it is nothing but a multiplier of kn and values. Right. Now W14, it means that kn by capital N, it is 1 by 4. Okay. And if you get a value, say 4 means we are performing 4-point DFT. When we have say 8-point DFT and you get a value 2 by 8, it is again W1 by 4 because it is in the this top by bottom. Okay, so it is again 1 by 4. So W14 is equal to W28. Okay, so that you need to keep in mind. W02, it is equal to W08 because Kn is equal to 0, right? Kn is equal to 0. So 0 by 2 or 0 by 8, again it comes up to be 1. So some of these things you should keep in mind. Now why I told that you should keep that in mind, this is because we may need it to understand the 8-point DFT. Okay. So herein, if you see, it is given W08. So you can go for the total factors in this fashion. But what I prefer personally is that suppose you are having over here W0. We are performing 2-point DFT. We can replace this W08 as W02. Okay. So everywhere we can replace it. Then when we are performing 4-point DFT, if you see, it is saying W08, W28. So I can easily replace it at W04, 2 by 8, W14. Why? It makes my life easy. Okay. So again coming over here, when I am performing 8-point DFT, I can keep it as W08, W18, W28, W38. Okay. So again, what I am trying to say is that you can use this nomenclature also W08, W28, but personally I feel comfortable to put up the total factors in an easier fashion when I am performing the longer numericals. So when I am performing 4-point DFT, it would be fitted in my mind that I just have to put the serial numbers W0123 in that fashion. I will put it. Okay. Now again, if you see, we are having this 2-point DFT. Since we are doing 8-point DFT, see, we are performing 4 2-point DFTs. Okay. Now, after that, if you remember, we performed 4-point DFT. Same thing we did here also. We will be doing the same thing, right? So over there we said that this is the middle point, and this is say 1 2 again 1 2, right? Same over here 1 2 1 2 out of the middle point. Okay. So now we have to do the thing for the 8 points in the final stage for an 8-point DFT or FFT. So which is our middle point? Our middle point is here. What do you mean by middle point? Middle point means we are just segregating the outputs into equal numbers in the top and the bottom. Okay. So again over here we will be having 1 2 3 4 Similarly 1 to 3 and 4. So 1 to 1, 2 to 2, 3 to 3, 4 to 4. Similarly 1 to 1, 2 to 2, 3 to 3, 4 to 4. And total factor, since it is an 8 point system, W08, W18, W28, W38. Okay, done. So we will be able to perform 8 point DIT FFT in this fashion. However, you will find that many of the students I have seen, they get confused, but most of the students, they are comfortable with the this signal flow diagrams or the butterfly architecture, and they do the numerical in that fashion in a better way. However, there are many students who are not comfortable with that. So for those students who are not comfortable with so much zigzag and all these things, I suggest them to do this numerical using this tabulation method. The same thing what we have done. So input has been put into the decimated order. Okay. Then in the stage 1, W and 2, 2 point total factor. This yellow mark areas, they would be having the total factor values. So first one is the 1, the top part. Second one is the total factor. Again, normal one, total factor 1, total factor 1, total factor. So you perform A dash equals to A plus B, B dash equals to, sorry, B dash equals to A minus B. Similarly, you perform the first 2 point DFTs 4 times. So see, got C plus D, C minus D. Similarly over here. Now, once we get this output, now this output should be divided into 2 to perform the 4 point DFT. So, see, the topmost parts, they are 1 and the lower bottoms are 1 minus J. Again, if we consider it as A double dash equals to A dash plus C dash, and the lower one would be A dash minus C dash. Okay. So similarly, this B double dash would be B dash minus J D dash, and B double dash would be B dash minus plus J of D dash, and similarly in the bottom half. And similarly at the stage third stage output also, the topmost parts it will be having ones, and the bottommost parts they will be having the one value. Okay. So it depends upon you what you want to do. Either you can do the method in the tabular form, or if you are comfortable with the this butterfly architecture diagram, you can perform the thing. Anyhow, those who are doing in the tabular form also, they need to at least draw this architecture. Okay, because this is the main architecture for solving the process. Okay, and then once you draw that architecture, then you can compute this in this tabular format. Okay. Now coming to the IDFT using DIT FFT methods. So what we do, same thing. The input now is your. I am talking about IDFT. Okay, I am talking about IDFT, inverse Fourier transform. So when we are performing the inverse Fourier transform, what is our input? Mm-hmm. We are having the frequency domains x of k. Now, what should be the input over here? We are following the using the DIT FFT method. That means your input is in the decimated order. Usually, why it has been developed? This has been developed because we want to do the forward transform, and hence from that name it comes decimation in time. Basically, decimation in time means your input is in decimated order. So when you are performing the IDFT using the DIT FFT method, we are using frequency domain signal, but it is an input signal now. Okay. Say x of n. What is the input over here? If you perform the DFT, xn. So xn is your input. So it should be in the decimated order, and your output is xk. It is in the normal order. Now, when you are performing IDFT, what is your input? Input is xk. Okay. Input is your xk. So input should be in the decimated order. Okay. So we have to keep in mind input is in the decimated order. So if you see capital X, capital 4, capital 2, capital 6, so this is in the decimated order. Okay. Since the butterfly architecture is same, there would be a subtle change. What is the subtle change? All the methods calculations it would be in a similar way. However, in the DFT we use total factors. Herein, while performing the IDFT, we will be using total factor conjugate. We will be using total factor conjugate. That means whatever is the complex this component, say a of j, it would be replaced with minus a of j and vice versa. Okay. So if you see in 2-point DFT, there are no conjugate values, so all are same. In the second case, if you see here, it was minus of j, this has become j. Again minus of j, it has become j. Then we have this 8-point DFT. See this minus, it has been converted to plus, and this minus again it has been converted to plus. Okay. This is the only thing which you need to do while performing the IDFT. Okay. However, there is another additional step. What is the step? If you see, we had a multiplier of 1 by capital N. Right? If you see in the DFT, yes. So, if you see over here, when we are trying to get to the time domain signal, 1 by N conjugate. Why conjugate we have got? This is the reason we have used the conjugate. Xn is the input. Okay. So this is an extra step which we need to add up over here. So in IDFT, it would be a 4-stage operation. So finally you have to multiply the thing with 1 by 8. Okay. Then only you will be getting the outputs. Okay. However, up to stage 3, the operation remains the same. DIF FFT, what happens? If you see, total factor has moved. Yeah. This one is in the normal order. This should be in the decimation order. If you have understood the DIT FFT, now you would be able to calculate these values. X0 is nothing but this is coming over here, this is coming over here, x0 plus x1, and then x1 equals to x0 minus of x1, and then after this addition is done, then we are having this multiplier of, with the total factor. Okay. Over there, before the addition, we were multiplying with the total factors. Right. So before the addition, we were having this multiplication with the total factor. Herein, after the addition is done, sorry, then we go for the multiplication with the total factor. Okay. So similarly, 4-point DFT mein, we will be having this Yeah, in 4-point DFT, initially we have to do the 4-point DFT, then we have to go for the 2-point DFT. Okay. Similarly, in the 8-point DFT, first stage would be the 8-point DFT using the FFT method, then 4-point, then 2-point DFTs, 4 2-point DFT. Okay. So in the DIT FFT, it was first 2-point DFT, then 4-point DFT, then 8-point DFT. Here it would be 4-point DFT, sorry, 8-point DFT, 4-point DFT, 2-point DFT. Okay. And your input order, it would be in the normal order, and the output would be in the reverse order. Now, herein, if you see the same thing, we have put it into the table. So, if you see the output, it is in the reverse order. It is in the reverse order. Now, while performing the IDFT, your XN, it is in the reverse order, because we are using the DIF FFT method. DIF, the reason remains the same. When we are doing the XN to XK, our XK is in the, that means the output, it is in the decimated form. So IDFT mein our output is XN. So this XN would be in the decimated form, and again there will be a multiplier of 1 by 8. Okay. So why FFT? Because in DFT there are complex multiplications which are equals to n square, and there are complex additions of n multiplied by n minus 1, where n is the length of the signal. Okay. However, in radix to FFT, the complex multiplication, it reduces to n by 2 log 2n, and complex addition, it reduces to n log 2n. So there are two methods of performing IDFT. So I have already told you xk as the, we take xk as the input, we take the conjugate w conjugate n, then we get the output in the reverse order or the normal order, whatever we talk about. So DIF FFT, it would be in the reverse order, DIT FFT, it would be in the normal order. However, there is another method where we can perform it in this way. First, we take the conjugate of the output. Okay, so we get xk, we find out xk conjugate. Then we perform FFT to get x dash conjugate n. Then we again perform the conjugate of x dash n to get x dash n, and then we calculate xn as 1 by n multiplied by x dash n. However, if you see, we have to take conjugates two times. Why to spend so much of time? So what we can do, we can use this method, take xk as the input, then you take the conjugate of the two factor values, and whatever the output you are getting, you just rearrange it according to the whether you are applying the DIF FFT or DIT FFT. So there are some numericals. Calculate 4-point DFT. So the signals are xn equals to 0, 1, 2, 3. So this can be broken down into 0 to 1, 3 in this order, and this is our values. So W01 is 1, W04 it is 1, W14 it is minus j. So you just put the values, calculate this, and you get the value. Okay. Now we can take this thing over here, and if we perform inverse Fourier transform, inverse discrete Fourier transform, we get back our original signal. Okay. So then this I have already told you about the LTI systems. So if you have a xn, yn, output will be yn equal to xn conjugate of hn. So how you can get it? You get that, do the DFT of xn, you do the DFT of hn, you get xk hk. So you get yk, which is equals to xk multiplied by hk, and after that you perform the IDFT to get the yn value. So this is what it is being written. So this we will start in the next class. So what I would say, request you, you perform this. Still, do we still have time? Yeah, we still have 15 minutes time. So please perform DFT of this signal by this matrix method, basic DFT method, and then perform this with the DIT method and DIF method, DIF FFT.